The broadcast is now starting. All attendees are in listen-only mode.
Hey, good afternoon, everybody. Thank you for joining our radiation safety webinar. Lori Siegelman is our senior consultant and our industrial hygienist here at W&M. Lori, thanks for joining us this afternoon.
Hi, good afternoon.
Before we get started, I just want to go over a few housekeeping notes. You will be able to ask questions throughout the webinar. I just wanted to let you know that if we do get an abundance of questions, to respect everybody's time, we'll make sure that we get to most of them. But if we don't get to yours specifically, I will make sure that Lori sees your question and that we'll answer all the questions through email. Also, at the end of the webinar, I will be sending out a certificate of completion, so you guys have some record of you attending. So without further ado, Lori, take it away.
Okay, all right. So today we have, there's quite a bit of information that you could cover in a primer or radiation safety topic, but I just want to cover three primary areas. We'll start out with the basics of radiation primer, just a little bit of covering what is radiation and radioactivity, so everybody is on the same page as far as terminology. And then talk a little bit about radioactive material and radiation in industry, some definitions, some regulatory definitions, and examples of what you might find in an occupational setting of why exactly you might be attending today. And then finally, a little bit of a regulatory overview for the regulations that apply to the various forms and uses of radioactivity, radioactive material, or radiation in Texas. So starting out with our primer, just differences between ionizing radiation opposed to non-ionizing radiation. So ionizing radiation, which is the focus of this talk, is in the short wavelength end of the spectrum. It's energetic enough to break chemical bonds and can cause damage to living tissue. And of course, then that's the reason why we're more concerned with ionizing radiation. On the other end of the spectrum, you have non-ionizing radiation. That would include things like your radio waves, cell tower emissions, things like that. On the other end are the long wavelength of the spectrum. And just as more of a visual representation, you have moving from the left to the right, which is from the non-ionizing toward the ionizing side of the spectrum, long to short wavelength. You have power lines, AM radio, FM radio, microwave radiation. Then you start getting into the shorter wavelengths of radiant heat, arc welding, X-rays, and then finally the ionizing part, the X-rays, gamma rays, theta radiation, alpha radiation, the ionizing type radioactive sources. So we'll start at the very basic, and I'm sorry if this is too basic for you guys, but I wasn't sure who was going to be on the call. An atom. So what is an atom? A small particle. Everything around us is made of atoms. Of course, if you're into the quantum mechanics, there's particles that are smaller, but we won't go there here today. You have quite a few naturally occurring elements, total of 109. That might be outdated information. They might have found some more by now, but the atoms are the smallest unit of an element that chemically behaves the same way as that element. And then the basic pieces of the atom would be the neutrons and the protons that make up the nucleus. And a shorthand way to write, so you have the chemical symbol, the large chemical symbol in the middle, and then the mass number and the atomic number. Mass number being protons and neutrons, the atomic mass, and then the atomic number representing the number of protons in the element. And it's important to know the number of protons. Based on the number of protons, that's what tells you what element it is. So nuclides is a specific particular chemical element. You can have different nuclides that have the same number of protons, say 6. As an example here, carbon-12 with 6 protons and 6 neutrons with an atomic mass of 12. would be the most common form of carbon, and that's the stable form. And then the radioactive or the unstable nuclide or species of that element, carbon, has 6 protons, again, the same because it's the same element, but it has 2 additional neutrons, so it's kind of neutron heavy. It's radioactive, and that's typically used in determining the age of archaeological artifacts, as everybody knows that. And all isotopes of the one element, as I said, have the same number of protons, but they might have a different number of neutrons. They have the same chemical properties, but they would have different radiological properties. So you have radioisotopes. Radioisotopes of the same species, say carbon-12 and carbon-14, will act chemically the same, but the different radioisotopes of a specific element will have different radiological properties, such as different half-lives, different types of radioactive emissions. The example shown on the screen is one of hydrogen. So you have the stable hydrogen with 1 proton and 1 electron. And then you have tritium that has 3, a mass of 3. So the hydrogen with 1 electron or 1 proton versus the tritium with 2 neutrons and 1 proton is going to act differently, and it's most seen in water, say in nuclear reactors. It's going to the radioactivity of the tritium is different than the radioactivity of the deuterium. Moving on. A little bit more about radionuclides and radioactivities. You have an unstable nucleus. Either it has too many neutrons as opposed to protons, so it wants to change the proton into a neutron. You can emit alpha particles or beta particles in order to get there and get to a lower energy state and balance the number of neutrons versus protons out. And in the process of doing that, and it leaves the nucleus in an excited state. Therefore, it needs to lose additional energy, often in the form of the gamma ray. And the gamma rays are the high energy, neutrally charged photons. Discrete parcels of energy. They don't have a mass and they don't have a charge. So basically, this is what happens when you have a radioactive material or a radioisotope that's unstable. With an unbalanced ratio of neutrons to protons, then it needs to release that energy after it changes by alpha emission or beta emission. And another way to represent that is you look at a graph that's graphing the different elements, number of neutrons on the X scale versus the number of protons on the X versus number of neutrons. And this is considered the line of nuclear stability. So the solid line at 45 degrees represents equal numbers of protons and neutrons. And so for the light elements, mostly below iron in the periodic table, neutrons and proton numbers are often equal. But as the atomic number increases, the stable nuclei gradually fall more and more above that line of V equals N. And without going into too much detail, this behavior is attributed to the attractive nuclear forces between the neutrons, or between protons and neutrons, or between 2 protons. This is a very, very extremely short range nuclear force, but it acts as an additional glue so that heavy nuclei with additional neutrons can stay together and be more stable up to a certain point. So what is radioactive decay? So if you have these unstable radionuclides with too many neutrons and they need to balance that ratio out, you get a spontaneous transformation called radioactivity. And again, I'm sorry if this is too basic for some of you, but we've just got a little bit more in this primer part. You have the unstable radionuclide, then you have the excess energy in the form of ionizing radiation that is emitted. And that would be considered or termed radioactive decay. You have different types of emissions. You've got the alpha particle, which is basically just a helium nucleus. It's mostly matter. It's slow and it's big. and it carries a positive charge. You've got beta particles that are equivalent to an electron. They're lighter and faster, medium-sized, and they carry a negative charge. Often, you're going to see a gamma emission accompany beta when the nucleus still has extra energy. Then, a beta particle is an electron, but the difference between an electron and a beta particle would be that the beta originates in the nucleus of the atom, whereas the electron, when it's emitted from an atom, usually it's not from the shell around the nucleus and not directly from the nucleus. So that would be the difference between an electron and a beta. Now, gamma and X-rays mostly are energy. They're really fast and really small and neutral, so they carry no charge. They can travel at the speed of light, and they cease to exist once their energy is gone. Some of the common alpha, beta, and gamma emitters I've listed here. And these are the common ones as they're used in industry, or they're used like in smoke detectors and things like that. The beta emitters are most commonly used to measure thicknesses of material or weights. They measure consistency between different materials or moisture content. Cesium-137, the gamma emitter, is a very common cancer treatment. It's also used to measure and control flow of liquids in a lot of different industrial processes. It's used in the food industry, food and beverage industry, to monitor the fill levels of packages. So, say for instance, Coca-Cola or Pepsi, any type of beverage. At the end of the line, you have the fill level gauge that monitors any cans that aren't all full, and then it will kick that out if there's less than full cans. Cobalt-60, another gamma emitter, is used to sterilize medical equipment in hospitals. It's also used to pasteurize certain foods and spices. It's also used to treat cancer, and it's also used to gauge thickness of metal in steel mills. And you'll notice here some alpha emitters are also gamma emitters, as we talked about before. For instance, americium-241. And then some beta emitters are also gamma emitters, for instance, cobalt-60. So there's 4 common measurements of radiation. You hear it all the time. You've got R and rad and RIM and Röntgen. So we're going to go over those really quickly just to get everybody on the same page of what all those different quantities and units represent. You can't detect radiation by your senses. You can't see it, you can't smell it, you can't really feel it in most cases. So an indirect method is normally used to measure the radiation, and that's dependent upon the creation of ions that occur when the radiation interacts with matter. Now, an ion would be an atom or molecule within the matter through which the radiation is traveling. So if you've got a survey meter, for instance, then the ion is created in the air. So it would be an atom or molecule that's lost or gained 1 or more electrons as a result of the deposition of energy from the radiation. So then it gives it a positive or a negative electrical charge, and then that way you can measure the radiation. And different measurements that we want to be concerned with, first and foremost, would be activity. How radioactive is it? How many disintegrations per second is coming from this radioactive material? And there are 2 different units that describe the activity. The most commonly used one here in the United States would be curie, and then the SI unit is the becquerel. Now, the becquerel is equivalent to 1 disintegration per second. It's named for Henry Becquerel, who shared the Nobel Prize with Pierre and Marie Curie for their work in discovering radioactivity. The Curie was named after Marie Curie, and she studied pitchblende and torbernite, which are uranium minerals. And I believe pitchblende is the photo that I've included on the slideshow here. The next unit of measure we want to go over really quickly is exposure. So you have how radioactive a material is. How many disintegrations per second is it emitting whatever radiation it's emitting, or radioactive betas or gammas or alphas. But what the strength of that radiation field at some point in air, you typically will measure it with a survey meter. That would be the exposure. Exposure, it's a measure of the strength of that radiation field at some point, usually with the survey meter, and it's most commonly expressed in units of R. So you have 1 R, or Röntgen. So Röntgen is abbreviated with an R. It's the amount of radiation required to liberate positive and negative charges of 1 electrostatic unit of charge in 1 cubic centimeter of air. It's named for the German physicist Wilhelm Röntgen, who discovered X-rays in the late 1800s. So once you know how much R, or how much, what your radiation field strength is in air, you can move on to what exposure would that be? Or what absorbed dose would that be? Exposure in air equates to the absorbed dose by considering what type of radiation you have. Is it an alpha radiation, beta, gamma? What type of tissue? The type of tissue that is getting irradiated will, the biological effect of that energy deposited in the tissue will change depending on what type of tissue it is. So for gamma and X-rays in soft tissue, the factor is roughly equal to 1. So you have, for instance, 1 R, 1 Röntgen produces an absorbed dose in soft tissue of about 1 rad. Rad, which stands for radiation absorbed dose. So 1 rad then in turn would produce a dose equivalent of about 1 rem. So rem standing for Röntgen equivalent in man. The absorbed dose is the amount of energy that ionizing radiation imparts to a given mass of matter. It's measured in units of gray. Gray is the SI unit. And then the more common unit that you might know of is the rad, radiation absorbed dose. And then the rem. Different materials receive the same exposure, but they don't absorb the same amount of energy. So in human tissue, 1 Röntgen of 1 R of gamma exposure results in 1 rad of absorbed dose, and then the soft tissue would again be a biological equivalent of 1, so 1, 1, 1. When you start getting into more sensitive tissues like bone marrow with more damaging radiation, for instance, like alpha, those numbers aren't going to be, 1 R will then not correspond to simply 1 rem. And here are some of the quality factors that you would consider, the different types of radiation, X-rays and gamma rays, and beta particles have a quality factor of 1, whereas when you get into neutrons and alpha particles, the quality factor increases. And what that simply means is that there's more damage as they interact with your tissue than if you just had gamma or X-rays. So to summarize that, the radiation type is important when you consider the interaction with the living tissue. Some types, alpha, have greater effects for the same amount of energy imparted. So an alpha particle imparting the same amount of energy is going to be 20 times more damaging than a beta particle. And that's because their energy is deposited in a much smaller area, as opposed to being more spread out with the beta. It kind of bounces around and departs its energy over a more broad area. So it doesn't do as much damage as just the alpha particle that deposits all its energy in one spot. So the unit used to quantify the dose equivalent would be the rem, Röntgen equivalent man, or the sievert, which is the SI unit. So that concludes the primer part of the presentation. And if there's any questions, I think Lance stated that you guys could type in questions or ask questions, and he will transmit those to me. I don't want to get too far along if anybody does have a question on that basic part.
Lori, nobody has any questions so far.
Oh, good. Okay. Cool. Okay, so really radiation or radioactive material is around us every day from a variety of sources. It's pretty much everywhere in the environment. We encounter it in just about everything. Some of the examples of how it's used in industry and commonplace things that maybe you wouldn't think about, pacemakers. That would be the top left-hand photo. Pacemakers sometimes use plutonium as a power source. Portable gauges sometimes will contain americium-241 or cesium-137. Smoke detectors often use alpha radiation to detect smoke particles. Commonly, it's americium-241, which ionizes the air between a small gap. And then current is passed through the gap. So if you have smoke particles, that current flow is reduced, which in turn then would sound the smoke alarm. And then Brazil nuts on the lower right-hand corner have a high level of radium and potassium, which are naturally occurring radioactive materials. Some definitions, when you talk about radioactive material and you get into the regulatory aspect of it, there's many different types of, or many different things that are defined for radioactive materials. So it, depending on your situation, may be very important to understand what the definition is of whatever it is that you have, because then that is going to dictate what rules to follow and what pieces of the regulations you need to fulfill. So radioactive material is a fairly general definition in the Texas regulations: naturally occurring or artificially produced solid, liquid, or gas that emits radiation spontaneously. So that's a pretty broad definition. But it could include other things which have also regulatory definitions, but I didn't put them on here for this presentation. You have byproduct material, low-level radioactive waste that, depending on what state you're in and what country you're in, can have a variety of definitions. Source material and special nuclear material, just to name a few. But the most common that you would see that would require a license or is regulated would be the byproduct material, and it can be in the form of a sealed source or unsealed sources. Unsealed sources being, for instance, radioiodine, that you have a vial. If you have it open, you can spill it, so you have a radioiodine spill. Sealed sources, on the other hand, are encapsulated unless they're broken or leaking, can't really be spilled or distributed. So a byproduct material, it's used to describe the radioactive materials that are regulated and for which licenses are normally issued for people to use this material or to possess the material. Things or industries that are normally licensed for radioactive material or byproduct material include industrial radiography. You have gauging devices or gas chromatography and well logging. Production of consumer products such as smoke detectors or exit signs, static eliminators. Diagnosis and treatment of patients in hospitals when you were using radioactive material or sources. Colleges, universities, and then of course medical research and development. So all of those types of industries or types of activities then would require a license for the byproduct material. So sources of radioactive material can take many forms. There's mill tailings, uranium mill tailings. That's the upper left photo. It's not really clear on the screen. And then you have the sealed sources. What's shown on the screen is simply a really small, low activity check source that would come with a survey meter to check its operation, make sure it's working properly. And in the lower right-hand corner are brachytherapy sources or seeds that would actually be inserted into a patient with cancer at the location of the tumor, and then that seed would irradiate the tumor specifically right there at the source of the tumor as a form of radiation treatment. So those are just some types of radioactive material sources, and then of course those would need licensing and all of the regulations that go with the licensing. Another radioactive material source or source of radiation would be radon. Now radon isn't necessarily a licensed byproduct that you would follow regulations for, but in Texas it's not such a problem as it is in the Northeast, where you have basements and the formations there that lead to radium decays to radon and then the radon gas. It's a naturally occurring odorless, colorless gas that can get into your basement or seeps up out of the Earth's crust into whatever space you have, like a basement or a cave. What I've got shown on the screen is, and I think they even still do it, is they have these caves or radio spas that they call them, where they purposely go and they sit for hours a day for 2 to 3 weeks in a row to breathe in the radon, because they think it has medical therapy for instance, arthritis or asthma, respiratory illnesses. And so this is just a snip off of roadsideamerica.com advertising some radon health mines that you can go and visit if you're interested in. But it is a decay product of uranium. It's naturally occurring in soil, rock, and water. The inhalation of radon does cause health effects. Its daughter products, polonium and lead, are alpha emitters, and alpha emitters do a lot of damage to tissues, especially if you've inhaled them and then they're in your lungs. And there is a published action level for EPA of 4 picocuries per liter for residences. The next type of radioactive material or radiation we'll talk about briefly is NORM, naturally occurring radioactive material, which is very of great importance for those individuals who are in the oil and gas industry, petroleum industry, and drilling, where you have the produced water that comes up from the drill site. You have contaminated scales, contaminated sludge, and dust as byproducts of that oil and gas drilling. NORM originates from the disintegration of uranium-238 and thorium-232. Those radionuclides occur naturally in the ores, in the soils, in the water. And then during uranium mining or oil and gas drilling, you have that water that's brought up, or the rock that's brought up from the mining, that has then that uranium and or thorium concentrated. So it's more concentrated than it was in the ground. The groundwater that coexists with the deposits of oil oftentimes will have unusually high concentrations of the dissolved constituents that build up then during prolonged periods of the water-rock contact. And then when you bring up those waters, those produced waters that are particularly rich in chloride, which enhances the solubility of the radioactive element radium, that water then, you bring it to the surface, it comes up with the oil, you separate it, it's your produced water. You get your tanks and your pipes coated then with the scale that deposits radium in there. So you have NORM, which would be considered a type of diffuse NORM waste. So those are kind of the different types of radioactive materials or radiation. What I didn't mention and don't have a slide on is radiation producing machines that are also regulated by in the state of Texas. So if you have X-ray machines or XRF machines where you're measuring, say, soil, for instance, for lead content or heavy metals, those are X-ray producing machines. They don't have radioactive material per se in them, but when they're turned on, they generate X-rays. When they're turned off, there's no radioactivity and there's no radiation. But when you turn them on, like an X-ray machine or a other types of radiation-producing machines. In industrial radiography, for instance, that also is regulated. So the primary regulatory authorities in Texas include the Texas Department of State Health Services, Radiation Control Program within that group, the Railroad Commission of Texas, and Texas Commission on Environmental Quality. And we'll talk a little bit about each of those organizations in this section. First, I wanted to go over just a little comparison of what the radiation limits are compared to what types of radiation exposure everybody gets, just the general public. The limits for regulation of exposure, and this is above background. So above background, you don't subtract the background out or anything like that, or you don't add the background to it. The general public is 100 millirem per year. Radium in surface water and then radium in drinking water, there's limits there, and then that EPA action level for the amount of radon that can be in a residential structure. And a lot of times people will do a radon survey as part of a phase 1 or real estate transaction if there's a concern, or if there's certain, like a HUD real estate transaction that has that requirement to do the radon survey. And then if you compare those regulatory limits, then the general public, the surface and drinking water standards, to what kind of background levels we get every day just from terrestrial or background X-rays or cosmic radiation. When you go get a medical X-ray, you normally would get about 40 millirems of exposure. If you live at sea level, it's 83 millirem per year, just standing there from cosmic radiation. So that's just a little bit of comparison. What I didn't put in here is the limit for a worker. Worker limit is 5 millirem per year for a radiation worker. So some of the regulations that govern use of radioactive material or use of radiation-producing machines, manufacturing of devices with radioactive material, all of that. The federal regulation is the Atomic Energy Act of 1954, and of course it's been amended since then. But the Nuclear Regulatory Commission is the regulating authority. It was established by the Energy Reorganization Act of 1974. Kind of like the Environmental Protection Agency regulates the rules per the Resource Conservation and Recovery Act for hazardous waste. The same with the NRC. They regulate exposure and the use and production of the radioactive material. Some of the terminology, and we already went over this a little bit, but radioactive materials and terms included in the regulations that, again, it's very important to know kind of what your material is when you're looking at what regulations apply. Is it special nuclear material? Is it byproduct material? And then there's other definitions or other defined types of material here as it's listed. And orphan sources, there's a big initiative to find orphan sources. There's a lot of sources, sealed sources that have been lost over the years, and so those are referred to as orphan sources. A lot of times they'll show up at salvage yards and recycling centers. They get a source of radioactive material, sets off their alarms, and then that's what would be referred to as an orphan source. So radiation and radioactive material in Texas, as is stated at the beginning of this section, you have the TCEQ, Texas Commission on Environmental Quality, has primary jurisdiction over the extraction, the handling, the processing, storage, and disposal of radioactive material. The big one is the disposal, so they would be the one to issue license for disposal sites. The Texas Department of State Health Services, the Radiation Control Program within that group, has jurisdiction to regulate and license if you're going to possess radioactive material, use it, handle it, transfer it, or store it. That's their jurisdiction. Typically, they'll issue licenses, radioactive material licenses, for you to handle that, a specific license. and they also have generally licensed material. They do also regulate and register radiation-producing machines. So even if you just have one of those handheld XRF devices that generate an X-ray, it has an X-ray emission source there, those also are regulated and they need to be registered. Not licensed, but registered. So there's a registration application and then regulations that apply to that. And then finally, the Texas Railroad Commission, they regulate the disposal of the oil and gas naturally occurring radioactive materials. So if you have that produced water, you have the piping and the tank that have the scale that's formed inside, and so as a result you have worker exposure potentially to radioactive material. So the next few slides I'm going to talk mainly about radioactive material, not radiation-producing machines necessarily and not NORM, but just the radioactive material. So say, for instance, your facility that uses for research and development purposes some form of radioactive material, americium or cobalt or cesium or whatever, you need to have a license in order to use that material if it's above a certain exempt level. So if you have any quantity to speak of, then you'll need a license. And I've just put the regulatory citation here for your reference if you wanted to go and look at where all that comes from. But the actual regulations that you would be interested in looking at and what regulates that is the 25 Texas Administrative Code 289. And there's, about 4 different parts that you would mainly need to be interested in. 203 requires you to post certain notices and instructions. Part 226 tells you how to go about registering your radiation machines. Part 228 talks about the safety requirements for the machines. And then Part 231 will tell you that's your limit. Your workers can only get 5 millirem per year, et cetera, et cetera. So I did include radiation machines, I'm sorry. Those are the main regulations that you would be concerned with if you have, say, a cabinet X-ray machine that you use for non-destructive testing, for instance, or the XRF machines. When you have the actual radioactive material where you need a specific license, so you get that license from the Radiation Control Program, and you would need to look at the Part 252, licensing of radioactive material. And that contains all of your regulations specific to the licenses. And then you have others. The other parts regulate your worker exposure. If you have a license for radioactive material, one of the differences here, the main difference is you have to have a radiation protection program, a written program. In the statement or the verbiage in the regulations is it needs to be sufficient to ensure compliance with the provisions of 289.201. 201, so depending on what it is you're using, how you're using it, how you store it, that's going to dictate how detailed your radiation protection program has to be. And then the Part 202, again, protection against radiation, that's your worker standard. How much can they breathe in per quarter? How much can they breathe in per year? How much dose can they get? Total dose over a year. And then the notices, instructions, and reports is the same as for the radiation-producing machines. I've included just a quick outline of what you might consider the major elements of a radiation protection program. One thing I'll point out is the second main bullet on the left, the ALARA policy statement, as low as reasonably achievable. That's a very common term used in radiation safety world, and that just because the limit is 5 millirem per year, you still can't let your employees get up to that limit of exposure. That's the philosophy is that if you can control that exposure more, that it needs to be controlled as much as feasible. So as low as reasonably achievable is the worker exposure and the general public exposure that you have to work toward. So really the 5, or of course lower for general public, is like a not to exceed, but it's really as low as reasonably achievable. So if there's something you can do to make it be lower, you're required to do that. And here is just a summary. Again, this is for radioactive material licensees, not necessarily owners of radiation-producing machines, and it's really not anything to do with norm radiation either. So specifically, if you have a radioactive materials license, here are the main regulations that apply to you, the main things that you have to do. That would be have the license, pay your fees, of course, that's a big one, monitor your personnel, calibrate your instruments, do surveys, radiation level surveys, train folks, those postings. If you had sealed sources, there's some sealed sources that are exempt from this requirement, but generally speaking, every 6 months you've got to check to make sure they're not leaking, or every 3 months if you have alpha sources. In very strict control over your sources, your inventory, you can't lose them. You have to keep them locked up and under your control. That's very important. So the next and last thing I wanted to talk a little bit more about is the oil and gas norm, the Railroad Commission, and how they regulate. Their regulations are in the Title 16, Texas Administrative Code 4.601 through 4.632. The Railroad Commission regulates the disposal of the naturally occurring radioactive material produced during the oil and gas exploration and production process. So your produced water, your pipe scale, your tanks. Their provisions do not supersede the rules of the state health services that we were just discussing. In fact, if you look within, for instance, 4.608, pulls in the worker exposure limits and the radiation protection program requirements and all of that from the state health services standards. So you still have to protect your workers, and this is in a case where you have, say, a pipe yard that you're offering as a service decontamination of your pipes. So an oil and gas drilling company comes and takes their contaminated pipes and delivers them, or has them picked up by a third-party service that decontaminates them. They get the scale off of the inside, they clean them up. So those workers at that disposal company or that pipe cleaning company are covered under the State Health Services rules for worker exposures. They're regulated by the Railroad Commission, but the Railroad Commission rules, as I said, pulls in a lot of the worker protection standards from the State Health Services. One of the bigger, more common requirements of the Railroad Commission is that norm-contaminated equipment must be identified. So if you have a compressor station, for instance, with tank battery and piping and this and that, you need to go ahead and do a norm survey. And if it's above a certain level of radiation exposure or radiation at the tank surface or pipe surface, then you need to label that equipment. It can be as easy as using spray paint to spray paint the acronym NORM on a piece of pipe, and then you have, of course, your survey report and things that go along with that. But that's one of the big things. So that contaminated equipment needs to be identified. There are some exclusions and exemptions within those rules, and actually there's a lot more to it than I've included on this one slide here. So if anybody is interested in getting more information on the oil and gas norm, Railroad Commission rules on that, I'll be happy to provide that later if you send an email. But I didn't go really in depth to the Railroad Commission rules here. And with that, that is really all I had. 45 minutes, so I'll allow for a few minutes of questions if there are any. And if there aren't, if you think of some later, just as Lance directed, send an email and we'll be happy to provide any additional information that we can.
We do have one question. Are there any tests that measure a person's exposure to radiation a cumulative exposure load?
Not really. Depending on the radioactive material, if you have an inhalation, you may be able to and you may be not, depending on what type of exposure it is. If you've had just an external exposure, say you're standing there and there's an X-ray machine, the X-rays or gamma rays aren't going to deposit anything into your system, so there won't be anything left over to measure. If you've had exposure to a radioactive material, so for instance, you work at a pipe yard, right, and you're decontaminating the scale, and you've inhaled some of that dust, then certainly there could be some tests that you could get that would possibly measure blood levels or something like that for inhalation because it's excreted. Maybe urine. I haven't refreshed myself recently on how the different radioactive materials move in the body, but depending on what the material is, it's going to act like that chemical in your body. So for instance, if you have a radioactive form of calcium, for instance, you're going to have a calcium, the radioactive calcium will adhere to your bone. So you can test it that way. Also, there are more, it's not common, and a person in the general public really wouldn't go to the doctor and ask for this test, but in the research field where they're looking for changes on the cellular level, sometimes with the lower level of exposure, whether it's internal or external radiation exposure, you can see very, very subtle changes at the cellular level when you've had radiation exposure. But that's not something that the general public would be able to get.
Okay, we'll wait a few more seconds to see if there's any more questions for Lori. It doesn't look like there are. Lori, thank you so much for the information. I'm sure that everybody enjoyed it, and I know I did. Anyway, you can see Lori's contact information on the screen. If you have any questions, you can definitely give her a call or email. If you have any questions about the seminar or like to maybe get the webinar and like to get copies of the presentation, email me at lfrench@wh-m.com. Lori, thank you again for the afternoon training.
Thanks.
Okay,
Everybody
you guys
have a good afternoon.
Okay, have a great day, guys. Thank you.